So some of this is my perspective over my career, which is, from my PhD, is about 39 years now. So, you know, a lot of this has been covered, but I'm going to get to some specifics. So there's a lot of debates that have gone on, and I'm kind of shocked myself that the debate over salts versus acid is still going on, because it should be a simple problem. And pretty much every case, the problem comes down to lack of lab data, lack of models, or both. And this isn't limited to spectroscopy. I see these debates at conferences in many fields. So, well, I'm going to concentrate on spectroscopy. I acknowledge that other fields need lab data too, and lab data is critical, and so are the models. So an analogy, I presented this at a Europa PSG, I think earlier this year. So you have a $2 billion mission to go find DNA of something like American Indian heritage around the world. But you know, DNA is nice, mature technology. But if you only have one DNA sample of American Indian in your database, how good is your $2 billion study going to be? Well, the obvious solution is not to throw out DNA testing, it's to collect more reference data. And that's the case that we're in you know, all our fields in planetary science. We're really starved for lab data. So early in my career, actually before I got my PhD, I was at MIT soldering a spectrometer together, and Bill Quaid and Bill Brunk were the program managers for planetary astronomy and planetary geology and geophysics. They were standing by my workbench, and they said, "We fund investigators at a minimum of $300K per year." This is 1975 or 76. Okay, put that in perspective. Today, that would be $1.4 million a year per investigator. So this is how far the program has sunk. So I put together a historical funding. The clouds here, blues are missions that are operational, greens are pre-launch. And this is all in FY18 dollars. I put in, if it's a line or a little circle, those are my budget numbers that I had at the time projected to 2018 dollars. So Galileo, pre-launch, $300K a year. Post-launch, this is for a co-investigator, not a PI, a co-investigator, on the order of $600,000 a year. So a lot of stuff got done. People had staff, grad students, technicians, lab support, programmers. We don't have that anymore. In Cassini, which some said was the last of the well-funded missions, well, compared to Galileo, it wasn't, but we actually got by. We did okay, you know, 70K equivalent before launch, and then during launch, between 200 and 300K. So we could actually fund some stuff, and we've accomplished a lot. Cassini was a very successful mission. So we need to at least maintain Cassini level funding as big missions go forward. And traditionally, little missions like MGS and other newer ones are lower than this. Well, back in Mariner 9, I don't know you'd call that a big mission or not, but it was certainly a lot better funded. So starting around 2000, the budget per investigator really dropped. And I will argue that it is that drop over the last approximately 20 years that has really impacted lab work and modeling, and so our ability to interpret new data. So we, like Cassini, 13 years of data streaming back virtually every day, yet how many lab days were involved in interpreting that data? It's much, much smaller than 13 years of a big data dump. So we're still trying to interpret some of the Cassini data, and we will for many years at the rate we're going. Europa is a much, much harder problem with the radiation problems. So here's spectra of Europa, or all the Galilean satellites. And at this point in in, these spectra are 20, 30 plus years old. We shouldn't have any question marks. I mean, if we're sending a $2 billion mission, these should all be resolved by now. And they're not because we don't have the lab data and models to interpret them. Some of them are also, like the CN, that's actually not a real feature. That's an error in the calibration to the solar spectrum. So we were talking about that. That's the position of, there's an edge in the solar spectrum there that causes that. We had that in Cassini early on, but we figured out it was the sun. Real quickly, it turns out that Cassini, the major impact and interpretations that we were able to do were dominantly in the 2.5 to 5 micron region. This area is well studied, but I'll get into why the differences. And there's a lot of little features out here. And CO2, so here's Callisto, nice CO2 bands, and these side bands are interpreted as various things. We don't have enough lab data to be sure what they are, and terrestrial minerals have a lot of side bands. They're not what a lot of people are saying these things are. Today, we still don't know for sure what they are.
Right, you just said that the 4.57 is an artifact, though, due to solar calibration.
Well, part of it is the edge here. So what it really looks like, the calibration needs to be corrected.
Okay.
So if there's a feature there or not is hard to tell.
Okay.
In the UV is the least studied and has great potential. So unfortunately, this pretty much this whole region, we don't have a spectrometer on Clipper, but we do have IUE spectra, and here's Saturn satellites, and some of the similar absorptions occur on Saturn satellites that we're seeing on the Galilean satellites. Is this sulfur on the? We don't know. We don't have enough lab data. And like I said, the UV is really, really rich when we start looking at things, and a lot of organic molecules fluoresce. So if, some of these might be seen by the ISS. ICE instrument on Clipper, but it'd be nice if we had a spectrometer. As we go shorter, so where the Europa UV instrument is, we have even less data down here. We're growing in this region, so that'll help maybe interpret this 2.8 micron band. Going out into the infrared, so here's, these are Hapke models, so amorphous ice in the light blue, then the crystalline ice here, and then these are lab data. And we see that very oddly that the optical constants for crystalline ice don't match the lab data. Well, for a while I was wondering, could there be a wavelength shift in either the optical constants or the lab, but both are done with FTIRs. There isn't. It turns out that this is an error in the models. So how many people here knew that Snell's law is only an approximation? It's not a law. It's an approximation for non-absorbing media. Well, of course, this is an absorbing medium, and the rigorous solution for Snell's law was only published in 2009. And if you read this paper, if you send me an email, I can send it to you, or you can do a search, and these guys will be very happy to send you. They were real thrilled that somebody liked their paper. But because it's an obscure field, how many people really need this stuff? Well, we do. This needs to be coded into the radiative transfer models, and that's not done. Optical constants are very, very difficult to do. Whoever's done them, you probably know this, especially when you try and compare to somebody else who's made optical constants of the same material and you guys don't agree. That's very common. Well, for ice, does anybody know how many years Rachel Mastrapa worked on the ice problem? Because it is the best work that's ever been done for ice optical constants, yet it's still not perfect. And this is one example. This was in my 2012 Icarus Iapetus paper. So a Hapke model showed that the optical constants just didn't agree with observations, and it turned out that there was an error in correcting out the sinusoidal interference pattern that happened to be at a frequency similar to the 3.6 micron ice peak, so it didn't get corrected right. So the reflectance data helps to verify the optical constant data, and then the red line is where I derived it. And even my derivation, this is not right. So there's still more work to be done. There's also work in the near infrared. Is Mike Brown still here? Yeah. Okay. He showed high resolution spectra of Europa that had this 1.5 micron band kind of rounded, and but the positions are for crystalline ice. Well, why is this different? Also, well, this peak right here is an error in the VIMS calibration that's now corrected. We're up to RC19, but the optical constants don't match lab data in this region, and if we're going to detect trace amounts of organics in this region, we need that corrected too. So there's a lot of little details that need to be corrected as we're going to push to more limits and detect finer things. So in general, for those doing amorphous ice, there's band shifts at 2 microns, there's band shifts further out, there's band shifts here, and a lot of people just use a 1.6 micron intensity, but that doesn't work. When you have submicron ice grains, it suppresses this and changes the shapes here. This depression here is due to the presence of some fine grained materials. This shape here is, I've observed this in the lab, it's due to a grain size distribution. But there's other weird things that go on. And here's VIM spectra of Saturn's B ring. Well, notice, and there's fine grained materials in this too. What's weird, and I've never figured it out, and nobody's ever mentioned it, so I mention it publicly for the first time. We have a nice, and the wavelengths are right on. We have no issues with wavelengths for this data. So this band matches very nicely, but you can see this is shifted shorter than this. I've never observed that in the lab. What's going on with ice? Why is the ice different on Saturn's rings for just that feature and nowhere else in the spectrum? You know, is this an indication of cubic versus hexagonal or some other weird property of ice? I don't know. There's some interesting research for somebody. I probably won't have time to pursue it. So there's lots of little details that we still need to work out just on the basics. In the UV, we have only one set of optical constants at one temperature made by one person. I forget who it was, but this is a computation of a thin film, and then here's growing a thin film in the lab. This data doesn't match that. So what's wrong? Is this experiment wrong and there's some contaminant, which might be possible, or are these optical constants wrong? This needs to be repeated and verified, because this edge is used by the UV team. It was used a lot on Cassini, and on Cassini, we would have different groups making different interpretations because we didn't have lab data that went over the whole range. So the UV team would come up with one interpretation, the VIMS team would come up with another, and then we had the in situ instruments that would see something else, and trying to get them all to agree is really a challenge. And we're going to have the same problem on Europa and any other mission if we don't get the lab data to tie these things together. So, salts versus acids. I was frankly a little disappointed in this conference that I saw again and again and again mainly spectra out to 2.5 microns and not further. So the problem is that the 1.5 and 2 micron bands in water are the first combination overtone and have similar band strengths. So a lot of materials will show similar things. You broaden your wavelength range and you'll see differences. So for example, here's salts plus, well, H2O plus epsomite mixture. These are computed spectra from optical constants. And you see the salts have a huge peak here, just like ice does, but acids do not. And acids are what we observe. I mean, this is saying the strongest discriminators for salts versus acid is 2.8 to 3.6, 3.8 microns. So all your lab studies need to cover this range. It is critical that you do that. That's where the discrimination will happen. And this is what we learned on VIMS at Cassini also. A lot of things that I could fit all kinds of things if I only used the 1.2 to 2.5 micron range. I could have buried all kinds of things in Saturn's rings and the satellites. And if we go with the salts on Europa, that would be believable. You know, they like it. They want to see organics. I could have proven organics in Saturn's rings and so on. But it's all bogus. And out here tells the difference. Here's another example. Let's see, we have amorphous ice. So the band shifts that are going on are out in the infrared, are beyond 2.5 microns, are more telling. Even the shape of the 3.6 micron band is different with a funny peak and edge here. Some of this we don't know how accurate these optical constants are, because it's only been done by one group. So sometimes critical things like ice need to be done again to confirm it. So, but it's critical. And then all of this is incomplete because we don't have the UV. We need the UV also, because that'll tell us something else. Every wavelength region tells us something different. So we have some optical constants for the salts. So Brad's work here looks very good. Jim or anybody in the audience, are these data digitally available?
I'm not sure.
We need these digitally. So if you or whoever can search and see if they can find them, we need them. But more important, this needs to be done again, and 2.5 to 5 microns, and down into the UV. This is really important.
For this cleanup may be a good program, right?
Yeah, well, we tried.
Okay. Good. Good to know that you tried and you keep trying and
Working with Carly to.
Okay. So organic. So there's lots of commercial databases of organics, but they're not exactly relevant to us because they typically cover further infrared than optical remote sensing. And for ORS instruments on spacecraft, we need the coverage of 0.1 to 5 microns for Europa. I wish we were going out a little further, but that's okay. I mean, it's still, that's a great wavelength range and really will constrain solutions. So the other thing is transmission spectra are not complete for what we need, because transmission spectra, they'll tell you the strong absorptions, but in reflectance, we also see weaker absorptions because you penetrate deeper in. So for like your experiments, you find some feature out in the infrared due to some compound. The real question is, could we detect that with near infrared? So we really need near infrared reflectance of a particulate surface to see if the compounds that you're detecting or anybody else who's detecting lab work can be seen by either a telescopic instrument or a spacecraft. Because that's our ultimate. The lab data needs to be tied to observations. Otherwise, it doesn't really help us. So we have a growing library. This is funded by Cassini and the Cassini Data Analysis Program. We have hundreds of spectra in the visible to my work was out to 15.5 microns. And we also did trace amounts on a basalt so we could unsaturate the fundamentals. So we could see, we could then compare these directly to any feature that we observe in any spacecraft data or, well, yeah, for this wavelength region, it pretty much has to be above the Earth's atmosphere. And we did detect organics in the Saturn system, both on Iapetus and Phoebe. And in the plumes, there is a publication with Matt Hedman leading, or his, might be one of his postdocs, that has a hint. The data's a little noisy, but if we average more together, we might get it. But it looks like a hint of organics in the plumes. But you look at this, here's the Iapetus organics, and here's PAH. This is a Cruikshank et al. Paper. We can't actually identify what organic that is. We can only say it's consistent with a PAH. So why can't we detect it? We really need more lab data. Over the years, there's a lot of wrong interpretations, and I'll argue that the salts on Europa are wrong. But I'll caveat that in that once we get there with Clipper and the high resolution, we may discover outcrops of salt. So in the fine, even maybe in the NIMS data, maybe some of it is real. You've got to look at the 3 micron region. So just a little story with, when we went into orbit around Cassini, I gave the press conference the next day after we went into orbit, and we spent 2 hours the previous day with the press folks arguing over what I could say. And I wanted to say Fe2+. So I thought this was an Fe2+ band. It's not an Fe2+ band, it's actually a metallic iron, but I had the species right, just the wrong mechanism. They wouldn't let me say Fe2+. So the next day, after I actually stayed up all night analyzing the encounter data, after arguing for 2 hours, they finally let me say I could say dirt. So I got up in the press conference and said dirt, and then the next day on the Daily Show, they go, we sent a $4 billion mission to Saturn to find what? Dirt. So fortunately, things have been loosened up with the press people, and later we were able to get a little more sophistication in what we said. But the point was that initially we thought this was something in a Nature 2005 paper, I called this a CN band, and then when we analyzed more data in the infrared, there was no CN fundamental, and it took 7 years to figure out what this was due to, and finally figured out that it was trapped H2. So, so there's trapped H2 in the Saturn system. There may be in the Jupiter system with all the radiation. So yeah, not all the H2 may escape. So if it can be trapped either in ice or in one of the non-ice material, which is what it appears in the Saturn system, but it took a lot of lab work because we had no clue what to look for. So the radiation studies that would say what the products are. So you dehydrate something in the lab, we need to know what those products are. That's really important because that'll help guide what we need to do next. And when we do see something, it gives us a list of things to look through because the list is just too vast. We've gotten pretty sophisticated with, so if you go back, here's Phoebe data early on, and now here's the latest calibration, and the data are, it's hard to get lab data this good on surfaces this dark. And so we're getting all kinds of details, deuterium. This band here is carbon-13, so we're doing isotopic ratios. So it's getting pretty good. We still have question marks. Like this is a question mark. Not that we don't identify the band, but here's where VIMS has an order sorting filter gap. So we're not sure if the band is real or not. So if it's real, it's NH. But we just don't know if it's real. Just some other quick things. So we expect to get data of this quality from Clipper. And a lot of the solutions of what's there is going to come in the 2.5 to 5 micron region. So lab studies, again, in that region are very important. Now, not everything matches, and it's easy. If I restricted the solution from what I've seen here to somewhere in the 1 to 1.2 region out to 2.5, I could fit this spectrum beautifully down to the where you couldn't tell which line was which. But you start going further out and shorter, it becomes much more difficult. I didn't have a feel for this until I wrote a GUI where I could just slide all of these parameters. I can slide around and just watch the spectrum do things. And trying to come into a solution is really, really difficult over this large of a wavelength range. So in this case, I've matched this, and to do this, you need a submicron ice grain component. And it's not too far off out here. There's a big gap here. But a key here in understanding what's going on is, well, all of this, and I can fit this better. But notice out here, there's virtually no 1.25 band in the model and no 1.04 band. That's a key that says there's something fundamentally wrong with the model. And after some investigation, what it means is that we need layered media. So these wavelengths penetrate much deeper. So in order to get strong absorbers here, we need a frost on a larger frost or icy surface. And when I go back to lab studies I did for my thesis and published back in around 1980, you'll find frost on ice in some of my papers, and they do this very thing. So the models need to be upgraded to do layered media. HAPKI 2012 has some equations to do this. We have no idea how good it is because it hasn't been tested. So there's modeling that needs to be done. I've actually coded that, but I haven't had time to test it. And then in order to really test it, you need to go into the lab and construct a layered medium where you know what the layers are, take spectra, and test the model against that spectrum. There's a lot of work to do, and that involves both lab and modeling. So lessons learned from Cassini. We thought we were equipped with plenty of lab data, and we get into orbit and we see features we had never seen before. So we weren't as equipped as we thought we were. Going into Cassini, I didn't have a feel for how important the UV was, and it's far more important. And I encourage everybody to look at Brad Dalton's poster out in the lobby area there and see the paucity of UV data that we have. But the UV is very important. It's going to be important on Clipper, even though we do have a gap there, that because we have the short wavelengths that provides a strong lever arm for scattering and absorbers that we wouldn't otherwise have. I've kind of already discussed the hydrogen trapped in the 2.42 band. It took 7 years to figure that out. I initially thought it was organics, started an organics campaign. Nope. Let's see. There's a lot of compounds that are potential, like we do see organics, but we don't have a good match. So why is that? And then we have strange shape ice bands. We need more. Just on basic ice, we need lab data. We need lab data on high pressure ice. I actually have one measurement, and it is quite different. But it doesn't solve that one problem with a 1.5 band. And we need radiative transfer models. That's where this big wavelength region has really shown our models are inadequate. And all of this just isn't academic fitting a spectrum because it has implications to what is there and how we interpret whether it's habitable or not. How many knew that acids plus hydrogen peroxide is used by chemists to destroy organics in the lab? Yeah, so the chemists do. So, so it's important to know, we know there's hydrogen peroxide there. I'm really confident there are acids there. Those are not habitable environments. And so we need to know, are there places where these don't exist, where it is habitable? So knowing the exact chemistry is really important to answer those questions. And we can do it, we just need lab work. A quick thing on, once we understand a problem, we can do really, really impressive work. And the mineral spectra for Earth, Mars, terrestrial planets is very well known. There's still lab work that needs to be done, but it's not in the dire straits as outer solar system, and in particular, Jupiter system with radiation products. So here's, let's see, we have Phoebe and Iapetus in red and black, and we see a carbon-13. So we get the carbon-13, carbon-12, carbon-13 ratio, and Iapetus is similar to terrestrial. Phoebe's an outlier. This is a paper that's in review. It's been revised, and we're waiting to see if they're reviewing it again or will accept it. We also see OD. OD has very interesting properties in ice. So throughout the solar system, including Europa, we can get the DDH ratio. And so we've done this for the Saturn system. This is our 1 point with Galileo. All these green points here are the Saturn system, and it's not what is expected. It was expected that, and the models are saying the DDH ratio should be higher. Phoebe isn't just a bizarre outlier, higher than any comet, higher than anything measured in the solar system. It's not from around here. So you'll probably hear a press release when that paper does come out. So radiation, I've talked a little bit about radiation, but again, I'm going to hammer it home. We need any radiation products you do, we need to know what those signatures are that Clipper can get. And so that means your labs need to go from 0.1 to 5 microns. And 0.1 is very difficult because it's vacuum UV, but your samples are probably in a vacuum anyway, so you should be able to add on a vacuum spectrometer, and it's really important to get out to 5 microns. Spectral databases. It's easy to measure spectra and throw them out there. It's hard to document what you have. And for the USGS Spectral Library, which is dominantly just terrestrial samples at room temperature, although the latest one has a lot of cold temperature stuff, we've found it takes a person week per sample between, it takes, half hour or hour to make the spectrum, but getting all the documentation together and putting it all together into a package so that other researchers can be confident in what that sample is, it's a person week per sample. And that has a lot of implications for funding to get enough materials done so that we have confidence in our interpretations of spacecraft data. Then throw in radiation experiments, temperature experiments. How many people run days, weeks on a single sample? I mean, we need many labs doing this. There's plenty of work for everybody to do unique work. So unfortunately, in the review panels, there's a lot of infighting. I've seen and heard where somebody's dissing a proposal because they feel it is competition. We don't need competition. There's too much to do. We do need funding. So I've kind of covered this. Better labs. We have a lot of labs. Some of them have some capability, but not all. Those need to be upgraded. We need lab techs to continually churn out data. Our models need more rigorous development. And I've kind of done this, but here's the main things that we need, and then add radiation products on top of that. So it's a huge amount of effort that's needed. Let's see, conclusions. I've kind of hammered all of this. This slide was put out at a Europa PSG in 2016. Unfortunately, nothing's changed. We're 2.5 years later, nothing's changed. We need to push change rapidly. And then I haven't talked about spatial stuff, but an imaging spectrometer, which is what both the UV instrument is and the IR MISE is, you get the spatial context can give you new insight that a single point spectrum does not. And we'll have that. And that'll drive a lot more models, both geologic, chemical, and the insights will just explode if we have the lab data. Otherwise, we're just going to argue like we are today, or through this conference of salts versus acids. So I think that's that was my last slide. So with that, I'll take questions.
Any question for the speaker? Yes. John?
I was just wondering about a comment made yesterday. Could you give your thoughts on the detection of amorphous ice and the mapping of amorphous ice on Europa?
Well, the spectra I showed, a lot of the amorphous ice claims have to do with either the 1.65 micron band or the intensity of the 3.1 micron Fresnel peak. But in amorphous ice from the spectra computed from Rachel's optical constants, the Fresnel peak actually shifts, and there are several other indicators, several other things that shift in the spectrum. So you need to evaluate the entire spectrum, not just a couple of wavelengths. The whole spectrum needs to be consistent. And I've never seen a reflectance spectrum of amorphous ice that, to me, looked like it had any amorphous ice in it. In the literature, you'll find with Cassini data, several papers that claim amorphous ice, and those authors, I'm pretty sure they'll all agree now that there is none. And in fact, one of them was a Bonnie Barotti paper, and in the latest paper that I think just came out in Science, it was showing that it's all crystalline ice. So, and part of that was because it was an easy mistake because we didn't understand the impact of submicron ice on the spectrum that depresses the 3.1 micron Fresnel peak, and people thought that was due to amorphous ice. So yeah, you got to look at the whole spectrum.
I had a question about related to the layering that you were talking about. So with Saturn's rings, you're saying that I'm imagining then, I guess, that what kind, like the layers would just be layers of still water, right? So you're saying like grain size layer differences as you go deeper,
right?
And that could certainly have applications for Europa.
The Saturn's rings they call them particles, but these are many centimeter to meter sized particles, and then they have a regolith surface, so they're really like tiny moons to us as remote sensors. And so there's a regolith, and photons go in and they go down deeper and see larger grains. And that's true on all the satellites too. And if any planetary surface, any of you who do field work, next time you're out in the field, try looking at things as a function of depth in the top few centimeters, and you'll see there's a gradient in grain size and or composition. And we need to have that in our models because the spectra will show it.
Roger, wonderful talk. Thank you. You also mentioned in there organics of the fingerprint region in the 5 to 10 micron region, and how it'd be nice if maybe we had a space instruments that would observe out there. And we will. JWST will be able to, I assume, observe Europa at those wavelengths. So do you think we should...
As a single full disk spectrum.
It may resolve with the 8 meter.
No, not at mid-infrared because of the diffraction limit.
Okay, even 8 meters. Well, would that still be a case for laboratory measurements to cover that wavelength range? Because beyond 5 microns, or or not?
Well,
Okay, here's an
most-
opportunity. We don't have to then say, oh, we have to redo everything because we want to cover the 5 to 10
most
micron region too.
lab instruments that'll cover that range will also go out further.
But
So-
you have
so-
to have the right windows when you change.
Right, right, exactly. But that's not that hard. You should try and do it if you can.
As Reggie said.
Oh, Murthy was next.
Yeah, as Reggie, ooh, this one's Bob. As Reggie said yesterday, you have to look at the whole wavelength range in the mid-infrared to really understand what you're looking at chemistry-wise, so you can better know. That's one of those ways of characterizing the sample, so you can then give your reference spectrum where the instrument on the spacecraft is, and be very confident of what you're looking at in the lab.
Well, I would say you also need other analyses than just spectroscopy, because other things will tell you things that weren't exactly obvious in the spectrum, but once you learn that, you'll go, oh, that's what that is. So yeah, I mean, for the lab, it's multiple instruments to characterize a sample. Now, for organics, unless you're synthesizing them, you can go by, like by a Sigma-Aldrich spectroscopic grade, 99.9%. That other 0.01% could still be spectrally active somewhere, but you got to be practical on what limits there are to our resources. So you have to play that game.
Okay, Roger, a comment and probably a couple of questions. The comment is that you aptly touched upon how much efforts it takes to get quantitative values such as the optical constants. And Reggie has been talking about it for a long time as well. And we have actually worked on VUV spectroscopy of water ice and several other ice. The data has been there for the last 3 to 4 years, and we have not published it because we wanted to quantify and get the optical constants, which takes enormous amount of efforts. So publishing a spectrum is easy than to say that these are the optical constants. So that's one thing that everyone has to keep in mind. Yeah. And my question now is, if you put the 600K per year Galileo COI funding into perspective of what was the total cost of the mission, probably that would it make any sense, or
I don't know. I got numbers from people. Okay. Maybe not everybody got 600K.
Yeah.
But remote sensors on NIMS did.
Yeah. So you said, I definitely agree with you. This is one of the biggest problems
and I mean, to be honest, this was the Cadillac.
Yeah.
Maybe we don't need that, but we at least need Cassini and hope. This is proposed. This is proposed by one team, so not every team may be proposing this, and it'd be nice to be in this ballpark.
So if you want to do anything serious and provide serious data, as you said, about 2 to 2.5 FTs seems to be actually very realistic, which would mean about 600K in this, at least.
Well, it depends on where you're at.
Yeah, well, yeah. If not 600K, 500K, but it cannot be, let's say, 100K. You
That's
cannot
right,
pay,
exactly.
With 100K.
Yep.
Okay. So those are the, numbers that we are really looking into, and definitely it is not realistic to expect that that kind of funding would be available. And this is where probably we have to look for alternatives.
Yep.
Got a quick comment on the question too. With far UV, we are making measurements. We've done that with the Lunasols that we have in-house already. And then we're also making measurements of water frost. And there's a poster out there that has spectra out there. And so just wanted to make you aware of that.
That's great.
Yeah.
And for everybody making lab measurements, maybe some of this white paper stuff, there really needs to be a way to share the data. Obviously after you publish it, unless you're comfortable in releasing it pre-publication. But a big problem today is just, you see some spectrum in in some paper and you start making phone calls. You know, it'd be nice if there was a repository, planetary data system or whatever, but somewhere where it's easy to get the data. So if you're producing a bunch of UV data, yeah, I want to get a copy of the digital data when
I
you
sent
publish.
you the paper already. So, but the other question I had about is this crystallized versus amorphous ice. And I saw you put out some spectra out there where you see this small shift in the 1.5 micron band. It's about 50 nanometers, right? Is that? And now you say that is your indication of crystallized. It's not the 1.65 micron feature as much as that. And I've seen people go at other conferences, they'll quote you on that and say, there's crystallized in the PSRs of the moon. What's your thought on that? I mean, why would you weigh one shift versus...
Again, crystalline amorphous needs more than just the 1.65 band. You need to see other indicators if we go back. There we are.
Yeah, that's fair.
So while there's a shift to the 1.65 band, this is a much stronger band, and it shifts a lot. It shifts here, and somewhere I had the IR. You can see these shift, this shifts, and this peak shifts, and the shape of the peak shifts. So there's a lot of indicators to go after if you don't have some consistency throughout the spectrum. Now, you could argue that 10% amorphous ice and 90% crystalline, you might be able to hide it, but you know, if you're going to claim some significant fraction of amorphous ice, you should have some indicators at multiple points in the spectrum.
But could other factors be causing the shift?
What are the optical constants or the absorption of the UV absorption edge in amorphous ice? Is it the same or is it different?
But could other factors be contributing to that shift? Could like grain size or
Yes.
other content, because the ices are not often pure, right?
Right,
I mean, you have,
right.
So, all right.
The organics data that you showed for, I think, Cassini, are they available anywhere online? The reflectance spectra of organics. There were a couple of slides where you had a lot of organics.
Yes.
Are they available online?
Yes, they're in the Spectral Library 07.
Oh, USGS. Okay, thank you.
You know, if one of them, we didn't quite get everything in. I mean, I did a lot of measurements, and we didn't have manpower to document them all. So they're not all there, necessarily all there. I think all that were on that one slide are there. But if there's something that you need, contact me. You know, I may or may not have measured it. But if it's in a paper and you don't find it in the spectral library, yeah, I'll dig it out and send it to you.
I've got ones you might expect. I don't know. Do I have a microphone? Do I need a microphone? I don't know. But, this is very useful, very useful, very helpful with a dead microphone. There it is. Very useful and very helpful, even though I've got a dead microphone. But I'm just sort of scared silly about this water ice now. I've been saying for a few years that water ice is in good shape, and so I'm staying away from putting water in my spectrometer.
It's in better shape than most things. It's just not in good enough shape.
I mean, we just finished up doing, what did we do? I think we finished up doing nitrous oxide and acetone, you know, doing fingernail polish remover and laughing gas. I could have been doing water instead.
Yep.
And so,
yep.
You know, I remember talking to Rachel a few years ago about that. Okay, so get to the punchline without the baloney. So the punchline is that I remember that Rachel was talking about doing this in a way that I wouldn't have thought she was going to do it. It was computationally, she was going to go back and forth. She was going to go from her measured spectrum to a refractive index, and then she was going to publish her data. And usually what people do is they iterate. So I don't know how many people know about this, but I didn't know much about it till 10 years ago. You got two numbers. Anybody know what optical constant is? You do.
Yep.
A few people do. You got two numbers. This one depends on this one. This one depends on this one. And so if you measure this one and do a calculation over here, it affects this one over here. So you got to go back this one over here and recalculate that one.
Yeah,
and so they keep going back and
Kramers-Kronig
forth.
analysis.
Right, the Kramers-Kronig. And as I remember, Rachel went through this not with an iteration, but one pass. She measured the spectrum, knew the thickness, got K, calculate it in, publish the paper. And this is 7 or 8 years ago now, and so I don't know. That's one way to get some numbers, but I wonder if that explains some of the stuff up here. And nowadays, it wouldn't be that hard to go back if she has the data to go back and do the whole thing. Point number 2, and I'll shut up. Point number 2 is, as I'm standing here right now, I don't think there's a single computer program that's publicly available where you can go out and do the darn calculation and know what you're doing. There are people that have secret software. We used to call them programs. Now they call it code, I guess because it's secret. I don't know of anyone who has something out there.
All my stuff is online.
You have your code online to do? Okay, great. I will be glad to be corrected.
I don't have the very latest version, but anybody who wants to work with me, I call it research code, so it's not.
Well, we call it research because every time we use one, we have to go back.
So it's not trivial to work with, but I'm willing to.
So there's a group in South America that has something.
We have developed Kramer's coding regress analysis for UV spectroscopy, which can be used for any other.
So,
but I'm afraid to put it out.
There you go, right there, exactly.
Well, so early in my career, how many people remember John Adams? Yeah. John Adams is University of Washington professor. Not that John Adams. So he said, when you put out even an algorithm, publish it in a paper, somebody will abuse it and blame you. That shouldn't stop you from putting it out. Put it out. It's their problem if they screw it up.
So there's a group in South America that's published one within the last year or so, and some Cassini people are using it. So we tried it. I tried it. The first time I tried it, it crashed. So I got a better computer. Tried it again, it crashed. And then I got a better scientist. I got my friend to do it instead of me. And he tried, and it crashed. And this is one that Cassini people are using right now, but it's secret software. We don't know what it is in the software that's crashing, except it doesn't work. It's in Spectrochemica Act, I believe, or Earth, Moon, and Planets, or someplace. I don't know. Anyway, Perry Giaconis has put something together. I think he would give anybody here. He's written it in Python. I don't know what Python is except a snake, but he's written it, and he's got it, and he can actually calculate transmission and reflection spectra, and then we hope to publish it in the next year or so. It will not be secret. It will be available. Anybody who wants to use it, go in and play with it. I would love to compare Perry's results with what you have. That would be just wonderful. We don't know how Rachel calculated hers. Doug Hudgens, before Rachel...
Have you dug through her paper?
Yeah, we have, to publish them, unless she's done something since then. Doug Hudgens, who's at NASA headquarters, had a paper before Rachel. His was proprietary software from Nicolay or some company that's probably out of business now. So we don't know. We tried Doug's calculation, it failed. We don't know. And then we found out he had decimal place error. And it worked. Everything was fine on our software. But we need software, not just the data, but we need some software too. This is what I'm trying to get at here. We don't just need the data. We need the software to find out how somebody did something so we can reproduce it and verify it. Otherwise, you're just taking someone's word for it. And, you've been around this game long enough. You could probably come up with an example where a computer program was the cause of a lot of crying. I mean, Paul Romani told me there was one for Jupiter's atmosphere a while back, and they just found out after 20 years it doesn't conserve mass. Oh, good God, you can't conserve a mass, and you're using this. And there was just one in physics today. They're trying to work out the phase transitions in water, and it's all because of secret software that they disagree. So anyway, I would encourage you to put yours out, and I will shut up.
It is out.
Thank you.